Now we're going to learn the integration by substitution method. So we're going to find antiderivatives by a method called substitution, which handles a little bit more difficult problems to do. And then in Calculus 2 there's another method called integration by parts that you learn. But for now we're going to do the substitution method. So you take a look at a problem like this, find the antiderivative of x cosine 4x squared. Okay, so that looks pretty difficult to be able to do. So what you do is you try looking inside for a composition, the inside part of a composition, 4x squared, and you try calling that u. This method is sometimes called u substitution. They usually use the letter u, but w could be used or other letters. Then you take the derivative du with respect to x, and you get 8x. And then you simplify it to du equals 8x dx, which is a notational device really coming from this. Delta u, delta x is 8x, so multiply the delta x over and you get this. So that's where it's really coming from. So du is 8x dx. So when I look back in here into the original problem, I see the dx, I see the x, but I don't see the 8. I don't see this 8 right here. So we have to create the 8 to be there, like this. Now I have it, but I can't just go around multiplying 8. I got to remove it, undo it, by multiplying by the reciprocal on the outside of the integral. Because 1/8, you can factor out the 8, hit it with the 1/8, and it would cancel out back to the original. So you just take a quick check. Does this equal back to the original? Yes. Okay, so that's the method that we're going to use, where we create the 8 and remove it. Alright, so now we're ready to convert over to u. So never have u's and x's together in the same integral. Never. So you never have u's and x's together in the same integral. You switch all the x's over to u's at one moment. So here's your dx and your 8x. So those two here become the du. Okay, that's the du. And the 4x squared is the u. So everything's switched over, lined up. Then you perform the antiderivative. So antiderivative of cosine u is sine u plus a constant. Now I'm calling it C1 because I want to make sure that, so we have this C1, I called it here, which is just a trick of the trade, because when you multiply in the 1/8 to the sine, you of course get this part. But then when you multiply it in with the C1, you get 1/8 C1, which I'm now calling C. So it just absorbs in to the C1 and it becomes a new constant, C. Some books don't even do the C1, but it is valuable because if you go into higher math, such as differential equations, keeping track of which constant is what is important. So it's a good habit to get into. Plus it bugs me to call 1/8 C C. Anyway, so this clears that up. So then here is the last step, is to take your u and substitute it back for what it originally was with x. So return to the x. And there's your antiderivative. Then of course you can check it, and when you differentiate, it all works out. As you can see with the chain rule, the 1/8 cancels out right here. That's why we're doing it. And you get back to the original here. Now here's another example up here. Negative 2x plus 3 to the 100th power. So you usually take the inside part of a composition and try that to be the u. There's your u. du dx is negative 2, so du equals negative 2 dx. Then I don't see the negative 2. I see the dx, but I don't see the negative 2. I have to create the negative 2 and remove it. That's the way we're going to do it. Create it and remove it. So it's negative 2, so I have to multiply it by negative 1/2. Then I'm ready to switch over to u's. Never have u's and x's together in the same integral. Convert everything over. So here is your negative 2 dx. That becomes the du, negative 2 dx. And this part inside here is your u. That's what's being called u. So everything is switched over. Now do the antiderivative, which is u to the 100th over 101 plus a constant. I'm calling it c1. Parentheses with the negative 1/2 on the outside. Then multiplying the negative 1/2, negative 1 times c1 became c. And then clean this up algebra and you get this. And I think you can see that if you differentiated this, use the chain rule, it would come back to the original function.